So in this problem, we are going to see which of the following sequence or sequences, maybe one, two, or all three, will lead to the chemical change as we have seen here. So you're going from this alkene ketone to this conjugated diene with a side chain and a aldehyde in that. Okay. So let's see. So this is a Grignard for sequence A. You're starting with the Grignard with an acetal group in the other end, and as you know, the carbanion is a very good nucleophile, and that is going to react as a nucleophile towards this ketone, and the expected product is going to be the alkoxide along with this 3 carbon chain and an acetal at the end. Okay, now when you treat this with concentrated sulfuric acid first, so concentrated sulfuric acid means you're using excess acid, which means you have obviously going to convert your alkoxide to the alcohol. So you'll first convert that, and then further concentrated sulfuric acid is going to convert this alcohol into a good leaving group, and heat is going to make sure that you generate the carbocation and you end up forming a conjugated diene, and you'll end up forming the conjugated diene, which means you will convert your alcohol to that. So, and then if you treat this with acetic acid and water, which is same as H3O plus that you have seen in the generic reaction schemes, if you treat your acetal with acidified water, what will happen is you'll convert your acetal to the corresponding aldehyde, because that's the alkyl chain and you have a hydrogen here, and those two oxygens will leave as ethylene glycol, and you are going to get the aldehyde on this 3 carbon chain. So 1 2 3 1 2 3 3 carbon chain, which means sequence A will work just fine the way it is written. Okay, sounds good. Now let's look at sequence B. So here you have a 1 2 3 4 4 carbon chain in your Grignard, which means again the Grignard is going to react with your carbonyl, and you are going to get double bond O minus alkene here. So double bond, so let's call this 1 2 3 4 A B C D, that is your 1 2 3 4. Okay, and then this is your A B C D. Okay, all right, so this works fine so far. And then what you're doing is you're treating this with concentrated sulfuric acid, which means again you're going to convert your alkoxide to the alcohol, and then further dehydrate the alcohol by making it a good leaving group, and you will end up getting your conjugated diene, which is going to work fine as well, and you're going towards your product as these two steps are indicating. Now what you're doing is you're cleaving, so you have 4 carbon chain, and in the product you only have 3 carbon chain. That means you have to cleave off one of the carbons, and that can be easily achieved using ozone and DMS, which is what you call ozonolysis. So that carbon will leave as formaldehyde, and this carbon now is going to have a bond with the oxygen, a double bond. So this seems fine for the side carbon 1 2 3. Okay, now the only problem is your ozonolysis is not only going to cleave that carbon-carbon double bond, your ozonolysis is also going to interfere with other double bonds in the molecule, as you have seen in chapter 7 and 8 last semester. 7 or 8, I think it's 8, chapter 8. Okay, so it affects all double bonds. Therefore sequence B will not work as expected, because your ring alkenes are also going to be susceptible to ozonolysis. Therefore B won't work. A works, B won't work because of these two steps. Okay, all right, now let's see the last one. So here instead of a 4 carbon chain you have a 3 carbon chain. Okay, all right, so that is fine, I guess. 1 2 3 3 carbon chain in that regard. Okay, all right, so you convert your carbonyl to again the alcohol because of the Grignard reaction, and you have the double bond O minus, and then you have the double bond over here, 1 2 3 carbon chain, which is fine. And again you are treating this with concentrated sulfuric acid and heat, which means you'll make this an alcohol. More sulfuric acid will lead you to dehydration, will give you dehydration product, which is again going to be the conjugated diene. So far so good. You are getting towards where you want to be. So up until step 2, you are here. Now you are doing hydroboration oxidation, which means you'll get the anti-Marconic of alcohol. So what you're going to get is, if you treat hydroboration oxidation in terms of how this reaction sequence is to be achieved, you will get your anti-Marconic of alcohol on that carbon, and that is steps 3 and 4. Okay, and once you treat this with PCC, what will happen is you will convert your primary alcohol to an aldehyde without converting it to a carboxylic acid. You'll get that. But the problem is your hydroboration oxidation is not only going to convert your terminal alkene to the anti-Marconic of alcohol, it is also going to react with the ring alkenes. That is a problem. Just as your ozonolysis is going to react not only with the intended place but also in the other places in the molecule. Again, here we have no regioselectivity for just the reaction for where you want. It is going to react with other alkenes in the molecule. Therefore, because steps 3 and 4 are going to react here, sequence C is also not a suitable sequence for this chemical transformation. So it is only sequence A that is suitable for your chemical change.